Alright, welcome back everyone. In the previous video, we talked about the meaning and I tried to develop the intuition behind the gradient, okay? And we discussed that the gradient measures the steepness of a surface, okay? The steepness of a surface. This surface could be a mountain, alright? The surface could be a mountain, as we talked about. It could be a three-dimensional temperature plot, It could also be a three-dimensional concentration plot. So the gradient was used to measure the steepness at a given point, the steepness of these surfaces. Okay. Now we have to talk about divergence. What does divergence measure? Okay, that's the question we're asking. Before we before we dive into the intuition behind divergence, let's talk about the mechanics, the operations, the computation itself. Divergence is always applied to a vector field, and these vector fields can consist of, in our discussion, they're mostly going to be velocity profiles, but in general you can have electric fields. If you're an electrical engineer, you can have magnetic fields also if you are an electrical engineer. And the subject that we would be interested in is going to be velocity profiles, velocity fields. Okay, this is gonna be the star of our discussion. Velocity fields are gonna be the star of our discussion, and it can also be applied to various flux fields. Okay, flux fields, as we will study, as you guys will study in your transport phenomena class. You can have heat flux, mass flux, and yeah, momentum flux. Those are the three main ones. These fluxes will also be, each of these fluxes is a vector. Flux quantities are vectors, and when you will be observing fluxes in three-dimensional space, they're gonna form a vector field. So divergence is gonna help. I'm gonna show you what divergence is gonna tell you about those vector fields. Okay, here I have a very simple two-dimensional example. I have a velocity field. Okay, I have a two-dimensional, let me just point it out, this is 2D. I have a two-dimensional velocity field. Okay, and my horizontal component is both a function of x and y. Similarly, my vertical component is also a function of x and y. And here's the vector field representation. Let me just give it the coordinate system so that everything is complete. X, y, there we go. Now let's see what happens as we move in the x direction. As you can see, in the x direction, the arrows are getting bigger and bigger. Okay, so that would mean if the arrows are getting bigger in the x direction, that means the horizontal component is increasing as we move in the x direction. Okay, I hope this makes intuitive sense. As we are moving in the positive x, the length of these vectors is increasing, which means that, and it's increasing in the horizontal field, which means that the change in horizontal velocity with respect to x is positive. Now let's see what happens as we move vertically upwards. And as you can see there, the steepness of the arrows is slightly increasing. Let me add in other, just for completion's sake. The arrows are getting steeper. Okay, that means that the vertical component is also increasing as we move. That means the vertical component is also increasing as we proceed in positive y, as we proceed in positive y. Okay, so this right here is a divergent flow. The divergence, let me just write it here, the divergence del dot of VA is greater than 0. Okay, and we'll get to the computation in just a second. Now I'm just trying to develop the intuition. Okay, this right here is a divergent flow. Let me write it for you. So this is the mathematical notation, and it's telling you that you have divergent flow. Divergent, meaning there is more flow going out than that's going in. There's a net out. There's a net out. Net out. All right, those are just some of the terminologies, and I hope you guys are following. Next up, we have an other extreme, and as you guys can probably see, let me just give it the coordinates as well, x and y, the positive x and positive y. Now see what happens as we move in the positive x direction. The arrows are getting smaller and smaller, which means that change in horizontal x with respect to x, change in horizontal velocity with respect to x is negative. Okay, and I hope you guys can see that. Now what happens as we move in the plus y direction? You can see that the arrows are getting, the angle of arrows goes below horizontal. Okay, the arrows start pointing in. Now this means that the change in vertical velocity with respect to y is also less than 0, because the arrows start pointing inwards as you go upwards. The arrows start pointing inwards as you go upwards. And in this case, the flow is, if I were to write the mathematical expression, del dot VB is negative. Upwards it was positive, here it's negative. This means that in this scenario, we mean, when we say that del dot VB, or the divergence, is negative, that means the flow is convergent. Okay, now the opposite of diverge is converge. I hope you guys remember that. So this flow is convergent, and the meaning behind that is that there's net inwards flow. There's net inward flow. In the previous example, there was net outflow, as you can see, and I hope you guys can visually, intuitively feel that this is like spreading out. So there's a net out. Here it's going in, so it's converging, and there's a net inward flow. I hope that explains the intuition behind it. Now just to give you a feel for the operation itself. Okay, and now we're just going to talk about the computation, the operation, how to use the gradient. So let's say you have the vector field Vx, Vy, Vz, and the nabla, the del operator, we've talked about this. This is the partial with respect to x, partial with respect to y, and partial with respect to z. Okay, in Cartesian coordinates, of course. Now the divergence is actually a dot product. Divergence is going to be the dot product del dotted with the vector field, and this is going to come out to be, so now you just have to apply your knowledge from multivariable calc. How does a dot product work? And some of you have already learned it in physics as well. You guys should be familiar with dot products. So I have the dot product of the del operator with the vector field. Okay, and this should come out to be, I hope you guys are following, del, the partial derivative of x with respect to x, plus partial derivative of y, Vy with respect to y, plus partial derivative of Vz with respect to z. And that right here is how you're going to compute a divergence of a certain vector field. Okay, and this is going to be very helpful. This is going to be very important. This is very important to study fluid dynamics. Important in fluid dynamics, aka momentum transfer for some texts. Momentum transfer in some textbooks. Okay, now all right, just to give you guys a summary, earlier we talked about gradients. Gradients measure steepness of surfaces, mountains, temperature plots, concentration plots. In surfaces are the 3D equivalent of curves. I hope you remember that from multivariable calc. Now the divergence, what does the divergence mean? Now we can actually update this. Now let's update this. I'm gonna say that the divergence means the net outwards flow of a vector field. Okay, the net outwards flow of a vector field, and that vector field could be, those examples have already been listed here, as you can see. All right, net outwards flow of a vector field. And in case 1, I tried to show you what a divergent flow would look like. There's going to be a net outwards flow in this field. As you can see, the blue arrows, they get bigger in the horizontal direction and they get steeper as you go in the positive y direction. Divergent flow, the flow is diverging. In case 2, we had the opposite. We had convergent flow. The arrows got smaller and they started pointing towards a single point. As you can see, all these arrows, if I were to give me a second, if I were to trace their position, they're all trying to converge at a single point. So in that case, that was the other extreme. We have convergent flow. Both my partial derivatives are negative. And in this case, you have net inwards rather than net outwards. And then we talked about how to apply the divergence operator, how you're gonna apply it if you're given a vector field. So you have your vector field, you have your del operator, vector field, and you have your del operator, and the divergence is going to be the dot product of these two. Okay, the computation, as you can see here, the computation, give me a second. Yep, this right here shows you how to use this symbol, how you're going to be applying it to a given vector field. And yeah, this is going to be very important in our discussion of fluid dynamics and momentum transfer. All right, so thank you guys for your kind attention, and I hope this was helpful.